So I'd like to introduce Ron DiGiuseppe from Synopsys.
Thank you, Sean. And as you said, Synopsys is very happy to partner with ChipEstimate. You can see our booth is right next to the ChipEstimate.com booth. And as Sean mentioned, today's talk with Synopsys is about our automotive IP portfolio. Hopefully you saw yesterday we released a press announcement talking about our automotive IP. And today I'll talk a little bit about what was driving that decision for us to further invest in automotive and some of the market trends that are driving the high adoption in the automotive industry for semiconductor chips. So let's take a look at that first. And it's no surprise to all of us that the automotive semiconductor market is hot. You can see, of all the kind of major market segments, right now, automotive has the highest, fastest growth rate. Last year, it's $22 billion semiconductor market, growing quickly through 2018 to over $31 billion. So we all know that it's a big market, it's growing fast. And the other thing about automotive is there's many different applications for semiconductor chips inside automotive. From the more traditional applications on the right-hand side, such as body, chassis control, door locks, powertrain management. Also some of the new applications within power electric vehicles, hybrid electric vehicles. But some of the really exciting activity is on those left-hand side applications. Some of the new user interfaces for infotainment, a lot of the multimedia within the car, but especially some of the safety-critical driver assistance technologies. We've been hearing a lot about autonomous driving, semi-autonomous driving, but a lot of those advanced driver assistance applications, such as drowsiness detection, pedestrian detection and correction, surround view imaging, are driving a new class of chips. And those are the SoCs that I think we all need to be aware of as a community. What is required for those SoCs? So it's kind of exciting to have all of the new applications within automotive, and especially some of the new connectivity, such as 4G LTE cloud connectivity, Bluetooth connectivity with your smartphones. Those are also driving new SoC development within the automotive space. Then, we see a lot of new entrants into automotive, but automotive SoCs, it's not easy. You got to really want to be there. Some of the challenges, especially from a system level, is they're in safety critical systems. So there's a big focus on quality management and functional safety, and there's new requirements in the SoCs and the IP that make up those SoCs with regard to safety systems. And within a car, the user interface, the user environment is critical in making sure the driver and the passengers are comfortable in automotive. And it's kind of challenging though, because the user is targeted not just the 20-something teenagers that are very familiar with high tech, but you also have to have a user interface that is familiar to the grandmother driving a car. And having LCD screens and high-tech controls has to run the range of users. And so, who controls the user interface? Who manages user interface? Whether it's a smartphone connectivity and the new user interfaces like Apple CarPlay or the Google Open Automotive Alliance that are managing the apps on the LCD panel, or the more traditional, the OEMs that have their own, app management. So there's a lot of activities going on user interfaces. Then, of course, we all know about the electrification of cars, hybrid electric and full electric vehicles. There's a lot of sensors and a lot of power management within the cars. So that's driving a lot of electronics. But from a challenge point of view, it also shows that the chips that we provide are operating in very noisy environments and also operating in very high temperature environments. So these are all challenges we have to take into consideration when you're planning your SoC and you're building your SoC. And then finally, we all want to drive a car that's cool. There's a lot of new enhancements going on in the automotive industry. This is a picture of the Mercedes F-15. autonomous vehicle. It was showcased at CES in Las Vegas, driving onto the stage by itself. There's a number of concept cars driving from San Francisco to Las Vegas, like the Audi A7 concept. And you can see the demonstration, the automotive pavilion of the Delphi automotive autonomous car that's driven from New York to San Francisco. So these are the next generation of automotive. And as a chip industry, we need to understand what are the requirements at the SoCs that we're going to be developing for those applications. And it's a really exciting time in automotive. It's not just the new user experience. There's a lot of new trends. One of the trends is vehicle-to-vehicle connectivity, vehicle-to-infrastructure connectivity. The National Highway Traffic Safety Institute is mandating that vehicle-to-vehicle connectivity will be in your cars. And the idea there is to make it safer so that one car can talk to another, especially if there's a big rig in front of you, that your car can talk to the car in front of the big rig so they know what's going on in the traffic. Vehicle-to-vehicle is going to happen. It's being mandated by the government. And that's driving new radio technologies, maybe a new 802.11p Wi-Fi technology. So those are going to also drive semiconductor development for automotive. And with everyone having a smartphone, with cloud connectivity, either through Bluetooth or through telematics or through 4G LTE, that's creating a lot of other additional challenges in the automotive, especially in terms of security. Now, every car has security vulnerabilities, and us together as an SoC chip industry, we need to implement new security protocols, which traditionally have not been within automotive. One of the most popular automotive buses is the CAN bus within automotive. Every car has numerous CAN interconnect buses in the automotive. CAN's been around for quite a few number of years. It's totally unsecure. There's no security in the CAN bus. So you can imagine anyone breaking into your CAN network within your car has full control of everything within the car. They could, stop the brakes, push the acceleration, change all the door locks. CAN is an uncontrolled network, and every car has many CAN connectivity. So the car makers are relying on us to add security to cars. And that's a big new opportunity for us in the market to develop SoCs. And then finally, it's the self-autonomous driving, semi-autonomous driving, having the car drive yourself. Google cars, we've seen this, and that's going to happen in stages. We're not going to just go from driving a car to fully self-driving cars. It's going to be semi-autonomous driving, and it's already happening today. The self-parking cars, that's already a standard feature in a lot of cars, that's semi-autonomous driving. Now for me, I just kind of waiting for, I'm down in Silicon Valley, having a long, commute during bumper-to-bumper traffic. I just want my car to go straight. And that way I can do my email while it's driving. So fully autonomous, that's going to take a long time, but semi-autonomous, where in different use modes like self-parking or driving straight in a traffic jam, that's going to be happening sooner than you thought. And GM's announced their production vehicle that will do semi-autonomous driving as soon as 2017. So it's not that far away that you might think. All these technologies are creating demands on us as an SoC industry, and that's one of the things that's driving Synopsys' desire to further invest in automotive and to understand what are those requirements. Here are some examples of the SoCs that our customers are developing. Everything kind of in the dark purple is IP that Synopsys provides. And you can see from the more traditional MCU, where the processors run maybe 200 megahertz to 300 or 400 megahertz, for the kind of standard applications we know about, like chassis control, door locks. That's not as advanced technology generally uses E-flash, maybe 90 nanometer, 55 nanometer, going down to 40 nanometer E-flash. To the left-hand side, for kind of a high-end application with advanced driver assistance systems. And what kind of distinguishes an ADAS chip is it's going to be in an application where there's a lot of sensor data providing data, either radar sensors, LiDAR sensors, ultrasonic sensors, vision sensors, image sensors. And an ADAS chip not just collects that sensor data, it makes a decision and acts on that sensor data. So image processing, vision processing is a key, and radar processing is a key application within an ADAS SoC. And you got to think about a pedestrian detection where an SoC has to just process pixels, because images are just pixels. It doesn't know a pixel of a pedestrian versus a dog running by the side of the road or just a curb. It's all pixels to an SoC. So having an image processor engine, and Synopsys does provide an embedded image processing engine that can take all the images, train it for what you're looking for, and make decisions, analytics based on the images and vision images that it's receiving, is a pretty high, complicated, complex chip. We're talking gigahertz plus processing data rates, and lots of multimedia, lots of sensors. Sensor fusion becomes an issue because you have lots of image sensors, and as I said, radar sensors. So that class of chip with lots of multimedia IP, like HDMI for the LCD panel, MIPI interfaces for the image sensors, the embedded vision IP that Synopsys provides as well, Ethernet AVB to handle the multimedia connectivity. That's not your traditional mature SoC for automotive. We're talking kind of 28 nanometer class device, 16 nanometer class device going into automotive. And since these are ADAS applications, safety critical is important. And you can see some of the IP that Synopsys provides. Not only do we have a rich portfolio for sensor fusion, embedded vision processing, all the multimedia IP, we know that in automotive, it's not just having the portfolio, but making sure the IP is automotive grade. So we've invested to make sure our IP complies with the ISO 26262 functional safety standard. So if it's going in a safety critical application, we've already been certified for functional safety. And we know that our SoC customers need to qualify their SoC according to the automotive AEC-Q 100 standards, qualification standards. So having IP that's pre-tested for AEC-Q 100, and also having IP that meets the automotive quality standards, 16949 quality management systems. Those are what automotive semiconductor customers are expecting from an IP provider. And that's the kind of scope of the investment that Synopsys is making to make not just IP for automotive, but automotive grade IP that is ready for automotive applications. And this is kind of just that table of IP that we provide, not just the controller, digital controller, logic IP, but also the physical IP like USB PHYs and the embedded memories. These are pretty advanced chips that are running gigahertz class processor. So you're going to need external memory. So our LPDDR4 controller and our LPDDR5 targeting automotive applications, including the embedded vision processor, a sensor fusion control subsystem, analog, MIPI, USB. So the broad range of IP targeting automotive applications that we're enhancing with functional safety and quality management is kind of the key that we are investing in automotive. I do invite you to take a look in the automotive pavilion. We have a Synopsys booth where we have a demonstration of our embedded vision processor doing a speed sign recognition application. So a car driving through a neighborhood, identifying and tracking speed signs. And that's just an example of the high performance application that an IP needs to be ready for automotive applications. So this is my last slide. I want to thank you for attending. And we know that you're working closely with ChipEstimate.com is how we get the word out to the broad community of SoC developers. So if there